Oh, no. You don't pay taxes on businesses, or like, what about the businesses pay taxes? Oh. Like, Kevin has no say. Like, you should pay this. I think I took one question, and it was like, yeah, my man over here, you know, he gets it, yes. I missed it. I just remember the food for birthday. Some spaghetti. It was so good. What are you talking about? To you?
All right, we're getting into particle motion, which is big. Big. All right, so back to, I want to make sure that you can find the certain equations with respect to certain variables. So I'm looking at number 3. We talked about number 4 on Friday, but I'm looking back at number 3 now, and I'm going to let you finish up numbers 1 and 2. But if I want to know the area of an equilateral triangle, tell me how you find the area of a triangle in general. 1/2 base times height, right? Oh my gosh. Now, what if I asked you to write this equation using only, let's call this S for the side length, using only S? Could you do that?
Well, it's a 30.
Particle motion, area of an equilateral triangle is the question. Okay, so if I've got this equilateral triangle, right? Let's label it first. If I'm talking about base and height, right? This is the base. This is the height. Do you agree? But I want to write this, instead of base, I think I'll call this S, because I said I want it in terms of just using that side length, right? So I'm going to call it S. So here is S and S, right? How might I be able to write this equation using only S's? So now I've got 1/2, instead of base, I'm calling it S, because it's equilateral. How am I going to write that H using S's? Are you just guessing? I can do a right triangle thing. That's exactly what I need to do. So if I pull this triangle out, right? Look at this triangle within this triangle. What kind of a triangle is that? It's a 30, 60, 90. How do you know it's a 30, 60, 90? All the angles, that's right. Equilateral means equiangular, which means that this has got to be 60. Do we agree? All right, so I'm pulling this triangle out here. Remember, I need to know this using only an S, right? This is 60. That means this is 30. This is S. How do I find the missing sides? That's exactly right. So look, remember 30, 60, 90 triangle. All right, I'm gonna put some X's in here. Remember, we always go from the short leg, so I'm gonna set this triangle up the same way this other one's set up. If the short leg is X, that means the hypotenuse is twice the short leg, and that means the long leg is what? That's exactly right. X times the square root of 3. Now take this knowledge and apply to this triangle here, because it's across from the bigger angle. So think about it like they call it the hinge theorem. The bigger you make that angle, if there was a string connecting my two fingers, right? The bigger I make that angle, the longer that side becomes. So how do I know which side is longer? Well, the longer side has to be across from the bigger angle, right? Because there would be more string to connect my fingers as I make this.
I'm saying, how do you, what went through it, like, how do you know those numbers?
That's those two special right triangles we talked about Friday that you learned in geometry. Okay, so there's two. There's 30, 60, 90, which is like this. It always bases off the short leg. I would hear it.
Yeah, I was wondering.
Oh my gosh, y'all. All right, look. This is the pattern for 30, 60, 90, right? The small leg, we always work from the short leg and then back. Y'all didn't learn this in geometry?
I didn't learn. I had this fire. I didn't learn.
I like wouldn't remember like why would you
All right, so there's two types of special right triangles that you just have to memorize what happens there. We did it Friday. I think we talked about them a little bit, very briefly. All right, 30, 60, 90, there you go. 45, 45, 90, the sides are the same, so I'm going to call them x, and then you take whatever that side length is, and you multiply by the square root of 2. At this point in math, you won't always just be given this side or the short leg. You might have to make your way back to those places. So in other words, if I started here and need to get to here, I would need to divide by the square root of 2 instead of multiplying by the square root of 2. Or if I started here, then I would need to get back to the short leg again by dividing by the square root of 3, right? So now look at what I have. I have the hypotenuse of a 30, 60, 90 triangle, right? I need to make my way back initially to the short leg because that's what I base everything else off of is the short leg. So how do I get from hypotenuse to short leg of a 30, 60, 90 triangle? Divide by 2. So this side is s over 2, which makes sense, right? Because there's two of them and I've cut the middle. They're dropping that altitude. All right, s over 2. Now, no, it's okay. Now I need to rewrite that long side in terms of s. How would I do that? It'd be, that's right, I'm going to take this and multiply by square root of 3. So s square root of 3 over 2. Triangle using only s's, because now I'm back to this triangle, right? So this, okay, so area equals 1/2. What's the base? The base, well, the base is s. The base is s. So it's 1/2 base. Now what's the height? In the whole bottom here, right?
I don't really know how you got. Hold on.
1/2 base times height.
So how did you get S times square root?
Okay, I took the pattern of the 30, 60, 90 triangle, right? And I applied it to this triangle. Instead of having x's, I used s's, and I started with the hypotenuse. So starting with the hypotenuse to get back, is she back? She thought you were a teacher. Why is it over 2? It's over 2 because if I start from the hypotenuse, then to make my way back to this leg, I need to divide by 2.
Why is X?
Okay, so how do you get from short leg to long leg? No, look, tell me what's being done right there. Times the square root of 3. So I took the short leg and I times by square root of 3. Well, all you have to remember is this pattern, these two patterns. Why do I divide what? The base by 2. Sure? You get it? So now I asked you to write this using only s's, and we did, right? And I'm just going to clean it up just a little bit. The area of the triangle is s squared times the square root of 3 over 2. Agree or disagree? Oh, this became 4, sorry. 2 times 2. Top times top, bottom times bottom. Ooh, what's wrong? No, ask.
Why is there, why did you take the two out of the first and the nine? Why did you take the two out of the base, the not the nine, not the eight?
Sure.
Yeah,
Are you sure?
yeah.
Okay, that's it for what I asked you to do so far. But there's a reason we did this. So far, this is the algebra part. We haven't done the calculus part yet, right? Find the instantaneous rate of change. So I'm looking for the derivative, right? IROC is derivative. Find the instantaneous rate of change of the area with respect to the side length. So instantaneous rate of change of the area is the derivative of the area with respect to the side length. That's why I needed it to only have an S in here so that I could take the derivative. So what is the derivative? Y'all can do this, come on. This is what I would do on this one. I would change this to square root of 3 over 4 times s squared so that I could see it a little bit better. Because how do I find the derivative? All that's just gobbledygook in front of it, right? It doesn't matter what those numbers actually are right there because I'm still going to use the same process when I find the derivative of this s. In other words, that's when you're adding or subtracting up top. So this is going to be 2 times square root of 3 over 4 s, and I subtract 1 from the exponent. Y'all are looking at this like it is Greek. Well, I just came here, multiplied by this exponent, and then I subtracted 1 from it. I just wanted you to see before I clean it up where everything's coming from. Or if you write it like the other, s times the square root of 3 over 2. Yeah. Where did the 2 go? I got 2 divided by 4 is 1/2. So I did 1. That's fine. Yeah. No, because really this is just a coefficient, right? Because I'm multiplying, so I treat it like a coefficient. It still would because, so you did this times this and you did the product rule. So derivative of the first, well, derivative of a constant is 0. Two times square root of 3 over 4 would be 2 root 3 over 4. 2 divided by 4. I can divide them both by 2. Other questions about that one so far? I'm still in calculus land right now because I'm going to ask you what this means. That's the derivative. That's the derivative of the area with respect to the side length. But what does that mean? So it could be the slope of the tan line, but give me something in terms of rate of change, since I asked you for the instantaneous rate of change. What does this mean? What's the derivative of the area with respect to the side length mean? Give me, let's say that my side length was in inches, S inches. What would the units of ds, dA ds be? Inches squared per inch. Right, right. This is giving me the rate of change that the area of the triangle is changing as the side length changes. Okay. Okay, so because this is area, and if the side length was originally in inches, then the area would be square inches. If I was talking about volume, it would be cubic inches, right? And it's always units of this per units of that, top over bottom. Yes. Then for part C, it asks you to evaluate the rate of change of A when S equals 2 and S equals 10. Those are just plug in here, right? So dA ds when S equals, what did I say, 2, would be 2 root 3 over 2, which is just square root of 3. How about when S equals 10? 5 square root of 3 over 2. Oh, sorry. Yeah, you're right. You'd already divided it. Sorry. All right, so if this is a little confusing to you, it's okay. We're fixing to get to related rates, and it'll be even more confusing. So this will seem like 5 when we get there. It's okay. Try one more, though, before I talk about position, acceleration, and velocity. Number 2 asks you to write the area of a circle as a function of the circumference. So area as a function of circumference. So write the area of a circle using only the circumference as your variable. That assumes you know how to find the area and the circumference. Sure you do. What's the area of a circle? Right? What's the circumference of a circle? You should know this. 2 pi r, or pi times 10. Your geometry teacher needs to be beat.
It's like we learn it one time in class.
Okay, so I'm not saying that my way is the only way, but whenever, because some of these are so important, whenever I taught geometry, I gave postulates, theorems, and definition tests every single week, and they were cumulative. And it would always be anywhere from 30 to 50, and we had to have it every single week, and they would kind of interchange, but it built on each other. So when you left my geometry class, I guarantee you knew wrong. That doesn't help y'all. That doesn't help y'all because, yeah. Well, we'll do so much with circles in here that you should be able to remember this. But okay, area is pi r squared, circumference is pi d, which is the same thing as 2 pi r either way. So my question is, how can I write this using only the variable c? What's the variable that I got that I don't need? R. So how does R relate to C? C is 2 pi r. So R is the same thing as what? Close. C over 2 pi. Agree or disagree? I just took this and solved it for r, because what I'm going to do now is I'm going to take this and I'm going to replace that r with it, because if r is c over 2 pi, then I can just replace it. This really is related rates, but they've thrown it in here. Now I've written area using only circumference. I could, for right now, if I wanted to clean it up, I could. Pi times c squared over 4 pi squared. One of the pi's cancel out. No, it won't. What? Circumference measures the distance around the circle. Area measures how much space is inside. The length around the circle. If you took like a piece of string and wrapped it around the circle and then measured how long it was, that would be the circumference. All right, I'm going to... It's not hard. All right, here's motion. Here's the easiest way that I know to think about it. This is how I think about it. You start with this equation. We generally call it S of t, okay? And what that means is that's our position as a function of time. Okay? So what this is, this might be some random, I don't know, maybe 3t squared plus 5t minus 1, okay? And what this does is, let's say, come on, I plug a time in here. Let's say my time is in seconds, right? What this would do is this would tell me where my particle is after so many seconds, okay? And what I mean by that is I envision, I got my little ruler here because I think about a little bug, okay? Maybe he starts right here on 5, and whenever I plug in like 2 seconds, it tells me where he's moved to on this little ruler, okay? And this is important because in just a minute we're going to talk about how this changes. He can move forwards, he can move backwards, right? He can move any direction he wants. But this equation is going to tell me the exact point that he's at a certain time. Does that make sense? Okay. Then, this is the first derivation here. Then we can take this equation and we can tell how fast he's moving as he moves either left or right. Okay, and to do that...
Good morning, Camden High. This is Major Wallace.
So your chase is like that?
Velocity.
Velocity. Oh my God.
Velocity tells us about speed, okay?
That was just terrible.
Velocity can be positive or negative, okay? Of course, speed can't be negative, right? So the absolute value of velocity would give me my speed. But all that does, remember my little box is moving across? A positive velocity tells me he's moving forward. A negative velocity tells me, oh, he's moving backwards, right? But it's still tracking my little bug on my ruler, okay? To find velocity, all I have to do is take the derivative of position. So for this particular, easy peasy, for this particular example, 6t plus 5 would be the equation for my velocity. So I could tell if 2 seconds in, if my units were seconds for time, I could tell at 2 seconds exactly where he was and how fast he was going at that particular point in time. And whether he was forwards or backwards. Does that make sense? That's derivative of position. Position is where he is on this ruler. Well, I'd have to tell you at what point in time. Yeah, so like, where does he start? Well, he'd start at -1. You could, yeah. graph. You will, you will. All right, thing number 3 is acceleration. Now remember, each one of these is a rate, right? Other than this, if position, let's say position was meters. Let's say time was in seconds. Then my velocity would be in meters per second. Because it's a rate, right? My acceleration is a rate as well, and it is going to be acceleration in regards to time is going to be the derivative of velocity, which is the second derivative of position. In this case, I would have a constant acceleration no matter what time. It's always accelerating at 6 meters squared per second. No, it won't always be a constant. It's, yep, you keep adding. If I had one more derivative here, it would be meters cubed. If I had another, it would be meters to the fourth. Yeah. I tell everybody that all the time whenever we start practicing for the exam. Never leave anything blank. If you don't know what to do, take a derivative of something somewhere because you might get a point somewhere. But yeah, the answer's not always derivative, but a lot of times. And the first half, then we get into integrals. Then that's just the backwards of derivatives. All right, so how to tell if it's speeding up? And this, everybody always forgets this, and I don't know why. If velocity and acceleration have the same sign, in other words, they're both positive or they're both negative, that means my little bug is speeding up. I just always picture this little bug. I don't know why, but I do. And if they have opposite signs, I'm slowing down. Okay. No. 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 Great day. I literally just had it open. Finish. This is a graph of position. Okay, and this is not quite the nice quadratic equation that I had before, but take a look at this. This is S of t. Yes? This graph. So the first is, when is the particle moving to the left? Okay, so this is happening when? Let's think through this. When S of t is negative. Do you agree or disagree? Right? So when is it moving to the, no. It is slow. No, this is the graph of, so I need to know when velocity is negative. That's going to tell me when it's moving to the left. Right? 5 to 7. This part, because what are you looking at? You're looking for velocity, which is the derivative, which is the slope, right? So here, the slope is less than 0. The slope is negative, which means the velocity is negative, which means I'm moving to the left. So from 5 7. When am I moving to the right? Everywhere else? Whoa, 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 whoa. When it's flat, you're not moving. So let's think about this for just a minute. I stop and rest. I'm moving to the right. I'm moving to the right. I stop and rest. I'm moving to the left. How do I know? Because I'm looking at the slope of the lines that are there. If velocity is 0, I'm not moving, right? I'm just stopped. When it's positive, I'm moving to the left, to the right, and when it's negative, I'm moving to the left. So when am I moving to the right? 0 to 1, 3 to 4. And then 1 to 3. Y'all are getting this. 4 to 5. This is the actual problem. This is what you're going to do tonight. This is how we're starting with it. All right, so this one says to graph the particle's velocity and speed were defined. So let's do velocity first. We'll do velocity. Is it? Okay, so this is position, right? How does position relate to velocity? So this I need to do velocity, I need to do the derivative of position. Yes? Derivative is just slope. So I'm going to have to go back up to this. Let me zoom in a little bit. Ooh. And I'm going to need to do the slope of these little line segments, yes? So that I can graph them. Remember you did this on your quiz. So what's this, or some of us did this on our quiz. What's the slope here? I'm going up 1 over 1. So the slope is 1. Is it by 2s? Oh, it is. You're right. So it's slope of 2. Slope here is 0. What's the slope here? You're up 2, 4, 0. Let's see, down 2, 4 over 1, 2. Yes? So I'm going to plot this on this graph here. If you want a copy of the sheet, I can give you a copy. So from 0 to 2, I'm at 2. And then I'm at 0 until I hit 3. What? There's not an undo button on here? Oh, yeah, you're right. Straining to see these. Okay, it's 2 between 0 and 1. Then what? 0 from 1 to 3. Then what? Make sense? No, I'm not done because it also asked me to graph speed. What relationship does speed have? It's the absolute value of velocity. So which one? There's only one place that happens. This last one is going to become positive. That's going to be the only difference for speed. Oh, this is a close back. No, you can do them from No, we'll get to all that later. Right now, I just want you to be able to recognize them. All right, here's what I want you to do. Yeah. Yeah. I'm easing into this if you haven't been able to tell. talking about my relationship status on now. This, well, I'm glad I can help clarify some things. Some pictures, wedding pictures.